Imagine a place where every second is trying to erase you. Crushing pressure, endless darkness, absolute silence. And somehow, life chose to live there. In December 1872, the wooden corvette HMS Challenger slipped out of Portsmouth, England. Led by naturalists Charles Wyville Thomson and John Murray, its mission was to map what lay beneath the global ocean. At the time, humanity knew almost nothing about the seafloor. To measure it, the crew relied on a sounding line, a heavy hemp rope marked at regular intervals, and a newly invented Bailey device. This heavy iron tube used detachable sinkers. Once the weight struck bottom, the sinkers fell away, allowing the crew to haul the line back up. On March 23, 1875, southwest of the Mariana Islands, the ship stopped at a quiet patch of water known as Station 225. They dropped the weighted line. It kept going. 6 feet made a fathom, the standard nautical measure of the day. Hundreds of fathoms slipped through the crew's hands, then thousands. The line descended far past any expected limit, vanishing into the blue. Skeptical, the crew hauled it back up and repeated the drop. The second attempt confirmed the impossible. They had recorded 4,475 fathoms, over 8,000 meters of water. First called Swire Deep, then Nares Deep, before Challenger Deep became the standard. They had stumbled upon the edge of Earth's ultimate abyss. But exactly how far down did this dark scar truly plunge? Modern oceanographers have spent decades trying to pin down an exact number, converting a historical mystery into a complex measurement problem. Today, advanced multi-beam sonar and pressure sensors place the maximum depth of the Challenger, deep in a narrow band, between 10,935 and 10,984 meters. That is nearly 11 kilometers of vertical water. If you dropped Mount Everest into this abyss, its highest peak would disappear completely, capped by another 2 kilometers of icy ocean. The trench itself forms a massive crescent-shaped scar spanning roughly 2,500 kilometers across the Western Pacific, with a typical width of nearly 70 kilometers. A chasm so vast it could swallow multiple Grand Canyons side by side. Yet finding a single, absolute value remains elusive. Sound waves warp as water temperature and density shift. Tides rise and fall, and instruments must be calibrated against the crushing pressure. Rather than replacing the original witnesses, modern survey teams are refiners of uncertainty. What colossal force could produce such geometry? The answer lies in a slow, relentless collision far beneath the ocean waves. Here, the ancient Pacific Plate, a giant sheet of oceanic crust, roughly 170 million years old, is dying. It is cold, heavy, and incredibly dense. As it moves westward at about 8 centimeters every year, it collides with the younger, lighter Philippine Sea Plate. Unable to push past, the heavy Pacific Plate bends. It forces its way downward, plunging into the hot mantle of the Earth. This violent bending zone forms the V-shaped chasm of the trench. As this giant slab of crust descends, it grips the overriding plate, building immense physical stress. When the rock eventually slips, it unleashes powerful earthquakes that reverberate through the sea. The entire region is an active tectonic engine, part of the volatile Pacific Ring of Fire, with surrounding volcanoes arising from this same system. Above the subduction zone, a connected architecture takes shape: a forearc, a volcanic arc, and a back arc basin. They are all physically bound to the sinking plate, fueled by the forces of a planet recycling its own crust. But as this cold, ancient slab of seabed sinks kilometers into the Earth's interior, it does not travel alone. It drags down water, sediment, and chemical secrets. What happens when this descending slab begins to melt, and what does it bring back upward? Down here, hydrothermal systems, defined as heated fluids circulating through fractured rock, release unusual materials into the perpetual dark. Water escaping the descending oceanic slab alters the surrounding mantle rock through a chemical process called serpentinization. This reaction creates a buoyant slurry, fueling massive serpentinite mud volcanoes that carry deep geological material upward to the seafloor. Further along the volcanic arc, the chemistry takes an even stranger, more volatile turn. At the Champagne Field near northwest Aifuku, underwater vents release liquid carbon dioxide, which rises as highly concentrated icy droplets. Nearby, the Daikoku seamount hosts an incredibly rare, bubbling pool of pure molten sulfur. These intense chemical gradients and mineral-rich surfaces present a profound mystery. They are viewed as a possible setting for the origins of life and Earth's earliest metabolism, though definitive proof remains elusive. But can this harsh, toxic chemistry truly sustain living biology? At these depths, the water itself becomes an active enemy. Hydrostatic pressure increases continuously, squeezing every exposed surface from every direction with a force exceeding 1,100 atmospheres, over 1,000 times the pressure at sea level. Any gas-filled space is instantly crushed. Unprotected biological cells rupture, and conventional equipment is flattened. Ordinary submarines are useless here. They are not designed to withstand these forces. To survive, specialized vehicles must rely on pressure-resistant hulls, syntactic foam, and pressure-balanced components. Even a microscopic structural flaw invites immediate catastrophe. In 2014, during a deep mission in the Kermadec Trench, the unmanned research vehicle Nereus suffered a minor failure at nearly 10,000 meters. Instantly, the pressure triggered an inward collapse, obliterating the craft. While this loss illustrates the general risk of deep ocean operations rather than a specific Mariana incident, it reveals the razor-thin margin of safety. How, then, did a crewed vessel ever cross this barrier? On January 23, 1960, two men stepped inside a steel sphere just 2 meters wide, suspended beneath a massive tank of gasoline. This was the bathyscaphe Trieste. Unlike conventional submarines that rely on dynamic dive planes and rigid hulls to operate, a bathyscaphe is essentially an underwater hot air balloon, using lighter-than-water fuel for buoyancy and heavy iron ballast to sink. For Jacques Piccard and Don Walsh, descending was a slow, 5-hour plunge into absolute freezing dark. They were doing more than traveling distance. They were testing whether a human being could exist where physics says they should be liquefied. At 9,000 meters, a sharp metallic bang reverberated through the cabin. The outer plexiglass window had cracked under the immense load. They did not turn back. They kept going, choosing to trust the inner steel sphere to hold the line between life and instant obliteration. When the Trieste touched down on the silty floor of the Challenger Deep, it kicked up a cloud of white, powder-like sediment. Looking out into the spotlight's glare, they cautiously noted what appeared to be a flatfish, a highly debated sighting that challenged everything science believed about the limits of vertebrate life. But reaching the bottom is not the same as staying there. After just 20 minutes in the abyss, they released their iron ballast to begin the long ascent home, leaving the ultimate question of permanent life in the darkness below. 52 years passed before another human descended alone. In March 2012, James Cameron piloted the deep-sea Challenger to the floor of the abyss. Soon after, adventurers like Hamish Harding used modern vessels to repeat these extreme runs, relying on advanced acoustic positioning, carbon fiber, and synthetic foams to map the pitch-black basins. Yet, advanced design cannot guarantee safety. Thousands of miles away, in the cold North Atlantic, the 2023 Titan implosion near the Titanic wreck offered a catastrophic warning. At these depths, the tiniest structural fatigue is unforgiving. Engineering grants humans temporary, fleeting passage, but the crushing water pressure remains an absolute hostile constant. Below, in the freezing dark, only the adapted can truly stay. The transition begins at the surface. In the epipelagic zone, stretching down to roughly 200 meters, sunlight fuels a warm, crowded world of photosynthesis. Almost all marine life starts here, fed by the sun. But descend further, and the light begins to fail. By 200 meters, you cross into the twilight zone. Here, the ocean turns a cold, faint blue, stretching down to 1,000 meters. Only a fraction of surface light penetrates this space, and the water begins to chill. Then, the light vanishes entirely. At 1,000 meters, the midnight zone begins. It is a vast, freezing dark extending to 4,000 meters, where the temperature hovers just above freezing, and the weight of the water above starts to warp ordinary physics. Down here, the only illumination is produced by the residents themselves. Faint, cold flashes of bioluminescence generated through chemical reactions in their own bodies. Below 6,000 meters lies the absolute extreme, the Hadal zone, home to the oceanic trenches. Every meter of descent strips away options. The warmth is gone. The pressure increases by 1 atmosphere for every 10 meters. And food, which relies on organic debris drifting down from the surface, becomes incredibly scarce. Less than 1% of that surface energy ever reaches these depths. With the sun completely shut out, what force can possibly sustain life in the lowest valleys on Earth? To survive in the permanent dark, organisms do more than adapt. They solve fundamental physical equations. In the midwater depths, residents like the bristlemouth, pelican eel, and ghost shark exist as minimalist designs. In an environment where hunting is a rare opportunity, their bodies are built entirely for concealment, prey detection, and energy conservation. They rely on faint, cold, bioluminescent light and highly reduced, water-heavy tissues to drift silently through the water column, expending almost no energy as they wait for food to find them. But drop further into the true floor of the trench, and these strategies undergo a massive shift. Here, deep-sea gigantism emerges. It is not an absolute law of the deep, but a recurring pattern where certain species grow to unexpected sizes to cope with starvation. Among these are the giant amphipods, Hirondelia gigas, which scavenge the trench walls, processing scarce organic debris with specialized wood-digesting enzymes. Alongside them, herds of sea pigs slowly vacuum the soft floor, collecting nutrient particles from the silty mud, while enormous, fragile, single-celled organisms called xenophyophores build complex structures directly in the black sediment. At these depths, the sun is completely irrelevant to the flow of energy. Instead, chemosynthetic microbes fuel the base of the food web. They harvest chemical energy from geothermal reactions deep within the Earth's crust, proving that complex ecological networks can thrive without a single ray of sunlight. Yet, the ultimate boundary for complex vertebrates seemed absolute. For decades, scientists believed no fish could withstand the physics of the deepest zones. That boundary was shattered at 8,200 meters, where cameras recorded the Mariana snailfish. This small, pale, nearly translucent creature swims effortlessly, where the weight of the water would instantly flatten titanium. The snailfish does not fight the pressure. it integrates it. Its body has evolved to remove all gas-filled cavities that would implode under 1,100 atmospheres. More importantly, its survival is secured at the molecular level. Its cells are packed with a protective compound called TMAO, an osmolyte that stabilizes proteins, preventing them from being crushed and distorted under extreme compression. Without this molecular shield, the water pressure would force cellular structures to collapse, rendering muscles useless and shutting down vital enzymes. It is a solution written directly into their genetic code, allowing soft biological systems to withstand forces that destroy steel. But this molecular defense raises a more profound question. If life can adapt its very chemistry to survive the weight of an entire ocean, what are the absolute physical limits of terrestrial biology? In 1858, British naturalist Edward Forbes argued that the ocean depths were a vast, silent desert. Observing how marine populations thinned out in shallow dredges, he concluded that below 300 fathoms, existence became impossible. He called this lifeless zone the Azoic. It was a logical deduction for its time, built on the limits of early observations. But when later expeditions dragged nets through the freezing dark miles below, they hauled up living proof that shattered the Azoic hypothesis. The scientific debate shifted from whether life could exist in the abyss to a far more fundamental biological mystery. How do organisms maintain the basic machinery of cell survival under such destructive forces? Today, researchers still struggle to understand how membranes, proteins, metabolism, and reproduction continue to function in an environment that should instantly tear ordinary cells apart. The food supply down here is almost non-existent. Less than 1% of the organic matter drifting from the sunlit surface ever reaches the lowest seafloor. Yet, in this starvation desert, life persists. So far, scientists have cataloged roughly 400 species in the Hadal zone. But this figure is dated and revisable, a mere provisional baseline constantly rewritten as abyssal taxonomy struggles to keep pace with new discoveries. Many of these organisms are potentially endemic, locked away in isolated basins and found nowhere else on Earth. The truth is, we have barely touched this world. Most of our knowledge comes from repeated visits to a few highly localized points, leaving vast stretches of the Mariana Trench completely unexplored. Large areas of the abyssal floor have never been sampled biologically at sufficient resolution. In fact, due to the sheer difficulty of Hadal mapping, we have mapped the surface of the Moon and Mars with far greater precision than our own marine trenches. Every expedition to these valleys overturns another long-held assumption of biology, without ever closing the debate on habitability. The trench has shattered our old certainties, yet it offers no final answers. What else is waiting down there, surviving in the cold, crushing darkness of our own planet? We spend billions searching for alien life among distant stars, yet our own seabed remains a foreign planet. The abyss is a quiet reminder of human limitation. Every descent proves that nature doesn't conform to our rules, it rewrites them. What we discover next in the deep won't just change biology, it will redefine life itself. Share your thoughts on what lies waiting in the dark below.